Good morning, everyone. Thanks for coming to this seminar, which is part of our series of seminars, but certainly today is a very special seminar, and it aims to remember and highlight the scientific contributions of our colleague and friend, Montse Casas, that passed away on March the 30th. Montse was an active member of this institute, and she is the first of the scientists that has retired from the professional activity. In this case, this is a very sad retirement because we cannot anymore have her advice or her encouragement. Montse had a very long-lasting scientific collaboration with our speaker of today, which is Angel Plastino. I thank Angel for having very happily accepted to give this talk in memory of memoriam of Montse. Today we honor Montse, and so I will not give any further formal presentation of our speaker that anyway has been a regular visitor of IFISC and well known to many of us. The only thing I thought a little bit of how to say a few words about Montse, and I decided that the way to remember her today is just to share with you 2 email messages that she sent me on March the 10th. That was 20 days before she passed away. And those were messages sent from the hospital in Barcelona. I think they reflect so well her personality that they need no further comment. They were messages from Montse, the scientist, our colleague, and she was not using her position of rector of the university. The first one was asking for a visiting position for Angel this month of July. And she was just asking for an office at our institute for him, and she insisted that she would take care of all the bureaucracy herself, because she did not want to burden any of us with any extra work. And she ends with, I'll say it in Spanish, gracias, espero que te deje volver pronto. That was in Barcelona. The second one is from the same day, March 10th, and she apologizes for not being able to access from Barcelona the IFISC intranet because she didn't have there the passwords, and she was not able to update her contributions to IFISC annual report. And apologize again and sends me a list of these contributions. And the message finishes, again I say it in Spanish, with gracias por tu interés, quiero volver a la guerra. Just to finish, and as you can see here on the wall, the board of IFISC decided to honor Montse, giving her name to this seminar room that for any IFISC member it is known as the heart of most of our activities, and really what beats behind what can be seen from IFISC outside. So thanks for coming, thanks Angel, and we will see you.
Good morning. I thank the director of this institute, I thank him very much for giving me the opportunity to speak in this important occasion in which we are paying tribute to a great friend and a great scientist. And as you can imagine, Montse Casas worked for many years in many subjects, has a very, very long publication list. And it was impossible for me to just to summarize her work. Would take hours. So I decided on another kind of material. What kind of talk should I give that reflects some of Montse's contribution to science? And with my son, for both of us, she is our most important co-worker, with whom we have the largest number of fellows. Decided on this subject because it is the most cited among the many, many papers of Montse. The papers on this subject are the most cited. So that's an arbitrary criterion, but we have to do something. Okay, what do we mean by variable mass? Well, we are lucky in the sense that in many solid state scenarios, charged particles seem to move as free particles in a vacuum, but with a position dependent. This is a very lucky circumstance because, of course, nothing is nicer in physics than dealing with free particles in a vacuum. And with this trick of variable mass, we can do it in many cases. In nuclear physics, for quantum liquids, helium clusters, metal clusters, and quantum dots. This is the list of our papers on the subject. And as I told you a few moments ago, this one is the most cited concept. The Physical Review of 1999. Okay, then in many different instances, you can explain a lot of physics with this seemingly innocent equation, which is just Schrödinger's equation for a free particle, but with a position dependent mass. And this is not really trivial because the Nabla operator does not commute with the position operator. So when you take into account the non-commutation fact, this equation becomes something not so nice. Indeed, it becomes this. Where here we have the naked mass of the particle. This is an ordinary Schrödinger equation, but the potential W is this awful thing. Okay, that doesn't matter too much. This equation, even if the potential is awful, it works and explains a lot of things. So we are very happy with it. But the question we were trying to answer with Montse is this just a phenomenological equation, or it has a deeper foundation? It's just an ad hoc equation that we use because it gives nice results. And of course, we will use anything in physics that gives nice results. That's the first part. The second part is how does this equation connect with the basic principles of physics? Okay, so this is the first synthesis. The ordinary Schrödinger equation arises from this variational principle. You want this bracket to be stationary against small changes in the wave function. So the variation should be zero. And if you perform the variational procedure, you obtain the Schrödinger equation. What about this kind of Schrödinger equation with an energy-dependent potential? The same. The same variational principle that gives rise to the ordinary Schrödinger equation, which is this one, also gives rise to the variable mass Schrödinger equation. So this is a first principle equation. It comes from a variational principle. And then, of course, one becomes very happy because now this is not phenomenology, this is basic physics. However, since we during at least the last 15 years of our collaboration with Montse, we worked on what is called the physics of information. And we wanted some more basic foundation than this one, although this is important enough. We wanted it to work with foundations on information theory. I think this cannot be read. There was an important conference at the Santa Fe Institute in 1999 in which it was established what is called the Wheeler program. Which was summarized by Wheeler himself with a celebrated phrase that reads, "It from bit." Everything physical, according to this, to Wheeler and Kelman, who is the director of the Santa Fe Institute, everything physical is information in origin. Information comes first. Physics is a result of information. This may sound exaggerated, but okay, this is the program called the Wheeler program. I don't know if, of course, you have heard of Wheeler, but he is a really very important and distinguished physicist. He was the first to describe the fission process with Niels Bohr. He was the director of the doctoral thesis of Feynman. He made a lot of contributions to the theory of gravitation. And in the last stage of his life, he co-invented with Everett the theory of multiple universe. This is a foundation for quantum mechanics that people from philosophy tell that is the only one which has no contradiction and avoids the collapse of the function. That is also right. And another, this theory appeared in the doctoral dissertation of H. Everett, directed also by Rector. Okay, Wheeler proposed that all theories in physics should be derived from information theory, and that implies information quantifiers, of which there are two of them, entropies of various kinds. The Boltzmann entropy is the most celebrated one, but it's not the only one. There are infinite entropies, as a matter of fact, and all of them are used one way or the other. And there is Fisher entropy. Ordinary entropies are global in this sense. Information quantifiers are functionals of a probability distribution. Entropies depend on the whole probability distribution, but not on the details of the probability distribution. Local probability distributions depend on the derivatives of the probability distribution, and thus they depend on local details. So the Wheeler program implies that any physical theory should, at its foundation, have something to do with either entropies or Fisher information. So what we wanted to do with Montse is to see if we can derive this variable mass Schrödinger equation from Fisher information. Well, Fisher information is something not very complicated. If we have a probability distribution ρ, Fisher information is an integral that involves the derivative of the logarithm of the probability distribution. If you set the probability distribution as a product of two amplitudes, then Fisher information has a very appealing and simple form. It's the product of two gradients, which makes it clear that Fisher's information refers to the local content of the probability distribution. And Fisher information obeys this very nice relation between the variable x, which may be anything, under this integral, the variance of x should be greater or equal to the inverse of Fisher's information. This is an extreme universal relationship because it refers to any, absolutely any possible variable x, any possible probability distribution out of which you construct Fisher information. And why did we think of getting the variable mass Schrödinger equation from Fisher information? Because in the same year, in collaboration with two American physicists, Roy Frieden and Bernie Stoffer, Frieden is from Arizona and Stoffer from California, we have shown that the ordinary Schrödinger equation can be easily derived from Fisher information. As a consequence, it was natural to think that the variable mass Schrödinger equation should also be derived from Fisher information. So this is the way you do, you work. You have a Lagrangian which contains Fisher information, which is here. You vary the probability distribution, P, and you have the Fisher information, a normalization, Lagrange multiplier, and some knowledge, some expectation value that you know. The knowledge of this expectation value constrains the variation of probability. Actually, this variational principle was discovered by Schrödinger. Once he constructed his equation, he wanted to derive it from a variational principle, because otherwise it was a phenomenology. And he tried to see what kind of Lagrangian would yield his equation. And Schrödinger encountered this, but he didn't know what Fisher information was. So he discarded the whole thing, for which we are very grateful. You see, it's something really strange, because both Fisher and Schrödinger wrote their papers at the same year, 1926. But Fisher was a biologist, and thus he had no occasion to contact Schrödinger. If they had met, the physical information would have been born right there, not in 1989. But luckily for us, it is not me. And so we have a chance to do this. Okay, in this page we show how you can derive from this variational problem. If you choose conveniently what to put here, you derive from Fisher Schrödinger's equation with variable mass. Okay, the details are not too important. What is important is what kind of information you need. What we need in order to derive the equation we want to derive, that is Schrödinger's equation with variable mass, is to know the expectation value of the momentum squared times a scalar, which is the variable mass, the form in which the mass varies with distance. If you have that knowledge, you arrive immediately, but now from an information variational principle, to the equation that everyone uses. So now we have a double first principle foundation for this equation. One, the ordinary way in which Schrödinger equation is derived, and second, the equation can be derived from information theory according to the Wheeler program. Every important equation of physics should be derived from information theory, and this is absolutely true. The Klein-Gordon equation, the Dirac equation, the Maxwell equation, Newton's equation, all the statistical mechanics and thermodynamics, general relativity, all the equations of these theories are derived now, or have been derived now from information. Actually, now it is difficult to find some equations to derive from information theory because most of them have already been derived in that way. Okay. Now we come to the subject of supersymmetry, which is linked, as we will see, with variable mass. Well, you know, supersymmetry is something very nice that makes high energy physics extremely beautiful. Supersymmetry links bosons and fermions, which, if that symmetry did exist, would be partners. Of course, and regretfully enough, we do not find yet evidence in a Large Hadron Collider for supersymmetry, but one can always hope that it will be found. But it's extremely nice. In particular, the supersymmetry is imposed. Einstein's theory of general relativity is included automatically, and we have a theory of supergravity. So it would be really very nice if supersymmetry were to be true, were to exist. This is the history, brief history of supersymmetry. It was discovered by 3 groups independently in 1971. In 1981, supersymmetric quantum mechanics was advanced in a paper by Witten on the one hand and Cooper and Friedman on the other one. And in 1983, a very important concept, that of shape invariance, was introduced by a third author, Kennerstein. And with Montse, we were interested in, of course, in quantum mechanics and supersymmetry, to see how we could accommodate variable mass, not only with the basic principles of physics, but also with, if we could, that we did, of course, with supersymmetry. In quantum mechanics, supersymmetry made a great contribution because if we use the idea of supersymmetry, we can understand when or why a Schrödinger equation can be solved analytically. we all know, because we all have to study quantum mechanics at the school, that there are very few problems in which Schrödinger's equation gets a nice analytical solution. Harmonic oscillator, pool of potential, and so on. And that, more or less, all of it. Now we know that Hamiltonians that are amenable of an analytical solution for the Schrödinger equations are supersymmetric in the sense that I will immediately tell. So this is the basic paper on supersymmetric quantum mechanics of 1995. It's a very nice IFISC report. And after this paper, we can say that we have gained a deeper understanding of quantum mechanics, because we know why and how a given Hamiltonian is or is not susceptible of having an exact analytical solution for the Schrödinger equation. Well, supersymmetric quantum mechanics is abbreviated as SASI and involves pairs of Hamiltonians, not single Hamiltonians, but two of them, which are called supersymmetric partners, which means that there are supersymmetric potentials, one for each Hamiltonian. And this is the important thing. For every eigenstate of one Hamiltonian, its partner Hamiltonian has a corresponding eigenstate with the same energy. That is the extremely nice property. Partner Hamiltonians have the same eigenvalue. Okay, this is now we have two Hamiltonians, H1 and H2, with partner potentials, T1 and T2, and if they are supersymmetric, then there exists creation and annihilation operators, capital A, such that H1 is A dagger A and H2 is A dagger. We know this from the theory of the harmonic oscillator that we studied in the first course of quantum mechanics that we all have. But this can be generalized, considerably generalized. And we find this happy situation, then H1 and H2 will have the same eigenenergy. Here, of course, n is constant. What we did with Montse is to generalize the whole theory of supersymmetric quantum mechanics to the case of variables. Okay, if you in order for partner Hamiltonian to exist, it has to exist what is called a superpotential W, which arises as the exact solution of a Riccati equation. For example, this is at the bottom, equation 12 are the two Riccati equations from the partner potential V1 and V2. They differ only in a sign. And as you know, Riccati equations can be solved analytically. So if I know V1 or I know V2, I immediately can construct the superpotential W, and if I know the superpotential W, I can build up my ladder operators, A and A dagger. So you see, it is extremely simple. If you have the Hamiltonian, you construct from the potential the superpotential. Once you have the superpotential, you can get the other one, partner potential, and then you get the ladder operators, and if you have the ladder operators, you can write the Hamiltonians in the harmonic oscillator fashion, and then you have an exactly solvable problem. Of course, you are not always lucky enough that the Riccati equation has a nice solution that allows you to build the ladder operators, but in many cases you do. The result is that now, instead of having 4, 5, 6 simple Hamiltonians that have an analytical solution for the wave function, you have an infinite number of exactly solvable because of this nice trick of supersymmetry. Well, then, as I told you just a couple of minutes ago, what we did with Montse, continued with variable mass, was to see that the whole theory keeps working if we have variable mass, which it does. You have to do a few analytical computations that are included in just one page, and it works. So we really can extend all the ideas of supersymmetric quantum mechanics to the variable mass case. And you have all the nice properties, the common spectrum, which is illustrated here. You have two Hamiltonians, 1 and 2, and you have this relation. The eigenvalues of order n of the second Hamiltonians are the eigenvalues of order n plus 1 of the first Hamiltonian. And the only exception is the ground state of the first Hamiltonian, which has no partner. All this nice theory works in very different environments. And just last month, in June, some people published in Physical Review Letters a paper in which they show that they were able to construct waveguides that worked in this fashion. And thus they extended supersymmetry to optics. That is, they constructed with their hands supersymmetric waveguides. This is June this. The concept of shape invariance is something that comes together with supersymmetry and tells you which kind of potentials can be supersymmetric patterns. They have to fulfill this relationship. The potential V2 will depend on some parameters, a collection of parameters that we call A1. The potential V1 depends on a collection of parameters that we call A2. And if V2 is related to V1 in the sense that they are equal and the only difference is a term that does not depend on X and depends only on the parameters of V2, then V2 and V1 are supersymmetric partners. This equation 28 is the condition for two potentials to be supersymmetric partners. And this equality tells you that the shape of the two potentials is the same, and that is why people coined the word shape invariance. Then if you have shape invariance, you have partner potentials, and if you have partner potentials, you have supersymmetry. So, and this equation 28 keeps working if you have variable mass. That is what one of the things we showed with Montse. And the third and last issue I want to tell you about our work with Montse on the subject of variable mass concerns what are called hidden variables. The question is well known. You know that many people, but in particular Albert Einstein and also Schrödinger, were not happy with quantum mechanics. And they advanced the idea that quantum mechanics is an incomplete theory, that in nature there are variables that are hidden, that is, we cannot measure them, we cannot predict them, but these hidden variables make physics deterministic. So for many years there was a debate in which the big names like Einstein and Schrödinger were on the wrong side, so to speak. They were on the side that physics should be deterministic, and they could not accept the idea of, which is the basic idea behind quantum mechanics, that is that it is an undeterministic theory, and that this was originally proposed and defended by Niels Bohr. In 1935, a very famous paper appeared by Einstein, Podolsky, and Rosen, in which they showed that if there were not hidden variables, then action at a distance was possible. You see, after everything that Einstein has done, it is now happening that the most cited paper of Einstein is this one, related to quantum mechanics. And I mean, this paper is not cited by Einstein papers on relativity. It is unbelievable, but it's true. So, let's say in 100 years more, people will say, okay, this is the most important paper of science. It has 100 times more sites than all the others together. Okay, this was then a very interesting and important, because Einstein, Podolsky, and Rosen were showing that action at distance is permitted by quantum mechanics. And this has to do with what we call entanglement. Without hidden variables, entanglement implies action at a distance. That is what it was proposed. In the 70s, a Scottish physicist called Bell, as you know, showed that there are some logical inequalities that local hidden variables fulfill. A few years later, in France, in Paris, Alain Aspect made experiments that showed clearly that quantum mechanics violates Bell's inequalities, and as a consequence, experimentally it was shown that local hidden variables are impossible. This does not destroy Einstein Podolsky Rosen, because we still have the possibility of non-local hidden variables. And that David Bohm was able to construct a theory that is an alternative to quantum mechanics, which has hidden variables but non-local ones. So up to today we cannot decide whether Niels Bohr quantum mechanics or Bohm theory are one better than the other, because the pertinent experiments have not been done. David Bohm was a member of the American Communist Party, which brought him a lot of trouble. He had to escape from the United States, and actually was hidden he proposed hidden variables was hidden in Argentina, where the American many American Secret Service could not, were not able to find him. Eventually he went to England, and in England had no problems at all, and he developed his theory. And I tell you all this because we wanted to see with Montse if we could make a Bohm theory with variable mass, because of course Bohm worked with constant. Okay, Bohmian dynamics incorporates the whole Hilbert space formalism of the standard formulation. A Bohm particle has associated a wave function psi that obeys Schrödinger's equation. The new ingredient of the Bohmian approach is that a quantum particle of constant mass is also endowed with a definite position R, whose time evolution is governed as in classical mechanics by the equation dr dt equal p over m, where p is the particle linear momentum and has nothing to do with the momentum operator of quantum mechanics. And take here R, the position, is the hidden variable of Bohm. The result of a position measurement is regarded as predetermined because the theory is deterministic, but not predictable. In a way, all this is nicely written in a book by Bell himself of Cambridge University explicable and unspeakable quantum mechanics. Okay, so you see that the idea now is very simple. We asked with Montse, can we do everything that Bob did with variable mass instead of constant mass? And indeed we can do it. This is the definition of the moment in the Bohm representation. This is the linear momentum and this is the momentum operator. And this quantity defined in the equation 13 obeys a classical equation minus the gradient of potential, and the potential has the form of equation 14. And we were able to generalize the Bohm formalism. Here are some of the equations, which I will not detail, but we were able to generalize everything and show that the theory works fine for Bohm theory as well. So this is the moment of just giving you a respite because I'm finishing. So what we did with Montse with variable mass was first show that it can derive from a variational principle, the ordinary variational principle of quantum mechanics. Accordingly, the Schrödinger equation with variable mass is not a phenomenological equation, it's a basic equation. It comes from the same variational principle than the ordinary Schrödinger equation comes. Second, we also were able to show that we can derive the Schrödinger equation with variable mass from information theory. And this is particularly important in view of the Wheeler program. Any decent equation of physics has to be derived from information theory. And if it is not, then you better try to do it. Third, we have supersymmetric quantum mechanics. Since 1995, and we were able to show that we can add to supersymmetric quantum mechanics variable mass, and mass that depends on the position, and nothing happens. For Bohm theory, can be transcribed in terms of variable mass without any change. So the equations with variable mass were in the ordinary version of quantum mechanics and in the alternative version of quantum mechanics. And just to finish, a political note. I told you, Bohm was a member of the American Communist Party. The Soviet Union did not like quantum mechanics because yeah, this does not go well with Marxism. So it was unacceptable that the basic theory of physics would not be deterministic. They need something like that. And that is what Bohm did. they gave the Communist parties all the world at that time a basic theory of physics that was agreeable with the philosophy of Marx and of Lenin. But that this has to be taken seriously because we cannot yet decide which theory is better, Bohr's or Bohm's. And looks the similarity is not really nice. It's just one letter. So this is one of the pending problems is there are some people that believe that this never will be resolved, that there is no way of deciding which of the theories is the correct one, and we will have to accept that as a fact, which is not bad for us because it allows, if we have some idea and doesn't work one way, maybe it works on the other. Okay, this is just a small part of the body of work of Montse Casas. Of course, she did a lot of things in many other fields, but it would be unreasonable to keep you listening to me for it will be hours, so I better stop here and thank you very much.
Thanks very much, Angel, for your enlightening talk. I don't know if there are any questions or comments, including the political ones.
Yes, it's not about politics, but about information. What do you need to change? So, in order to derive from information theory the different equations, you need to fix the values of some expected values.
Yes.
To give information, what do you expect from some value? What is the difference to get the variable mass or the?
Oh, that's a very good question, which I should have said that. Here it is. For quantum mechanics, you have to know the mean value of the potential, and then you derive Schrödinger's equation. With variable mass, you need this, but also you need to know the expectation value of the variable mass times p squared. So you need more information to derive this equation than to derive Schrödinger's equation. But that is to be expected. If you have something more difficult, you need more input in the variation algorithm.
Yes, in the relation of effective mass, position-dependent effective mass with information, is it correct to say that for a position-dependent mass, you need information to be non-local, to be, let's say, not associated locally?
It is non-local, clearly. If you look at the equations, because you have the derivative here, you don't only have the first derivative of the mass, but the second. So it's not only the mass at this point, but what happens around.
So information is somehow
spread.
More questions? I have one myself. Why fission information? I mean, there are many information measures. Why fission one is the important one?
Well, that's a very deep question, but I can answer more or less quickly. If you use, let's say, the ordinary entropy, and you introduce this in the Lagrangian to make a variation, you get as an answer always an exponential function. The solution of the variational principle with the ordinary entropy is always an exponential function. You cannot get anything that is not an exponential function, which covers a lot of situations, but not everything is exponential. That's why Salis invented something a bit different, but he gets a power law. But if you change the entropy but keep the idea of an entropy related to the thermodynamical entropy, you keep having as a solution of the variational problem only a function, a definite type of function, but a function. But if you use Fisher in the Lagrangian, you get a differential equation. That is the variational problem in which the Lagrangian is constructed with Fisher information has as a solution a differential equation, which has a lot more freedom to work. And that's why from here you can derive Maxwell equations, for example, or the Einstein field equations, almost everything. Because if you impose the symmetries of the problem, you get the differential equations of that theory. For example, to get Maxwell's equations, you just have to impose that the Fisher information be Lorentz invariant, and that is enough, and you get the Maxwell equation from the variation.
Are there any further questions or comments? If not, I would like to close this, thanking again Angel for reminding us of some of the contributions of Montse to the advancement of science. I do believe that the advancement of science is a collective phenomenon, and I think she will be happy to see us all together here continue making our small contributions for the general advancement of physics and science in general. Thanks for coming, everyone, and there are some snacks outside.